So we're looking at the required practical to measure the current and potential difference characteristics for a filament lamp here. We've already done this for a fixed resistor where we measured the current and potential difference across the fixed resistor. We plotted a graph of current against potential difference, and we found that for the fixed resistor, the ratio of the current to the potential difference was always constant, and therefore we got a straight line that went through the origin. So what we want to see is whether it's the same for a filament lamp. So I've got the standard test circuit with a cell. I have a rheostat so that I can change my value of potential difference across the lamp. I have my ammeter to measure the current, my component that I'm testing, my filament lamp, and that's all in my series loop. And then in parallel with my lamp, I have my voltmeter. Now, what I'm going to do is I'm going to start with my variable resistor at its maximum resistance. So the current comes in, travels through the wires of the variable resistor and out through the top. So it's at its maximum resistance at this moment. So starting there, I should have my lowest value of potential difference and my lowest current. So I've got 0.14 as my potential difference and 0.08 as my current. That is my first value. Now, hopefully you've already got a table created in your book with a column for potential difference and a column for the current. Obviously, you need to have the units in those headings. And as we are recording, you must make sure that all your recorded data is to the same number of decimal places as the equipment. So if, for example, the potential difference says 0.10, you must write down 0.10. So let's have a look at that first reading again, 0.1514 volts, 0.08 amps. Second reading, we have 0.25, well, it's gone up to 8 volts, 0.09 amps. Third reading, 0.52 volts, 0.10 amps. Don't forget that 0 on the end. Another reading, 0.77 volts, 0.11 amps. Let's see if we've got any more in there. Here we go. 0.90 volts, 0.12 amps. Obviously, you can go back, reread, and rewatch the video to get those results again. Now, in order to get some more data to see what happens, I'm going to add in a second cell into my circuit. I've increased the resistance back to the maximum resistance. And what I might find is that my potential difference value is slightly bigger. So this is good. All right, we've got another set of data. Here we go. 1.07 volts, 0.12 amps. 1.12 volts, 0.13 amps. 1.23 volts, 0.1, we'll do that 0.14 amps, it keeps varying a bit. 1.59 volts, 0.15 amps. 2.04 volts, 0.17 amps. And we can see our lamp's got quite bright now. But I'm going to add in one final cell just to get some more data to see what our pattern is. So back to our maximum resistance. Now I've got 1.74 volts, 0.16 amps there. 0.09 volts, 0.17 amps. 2.33 volts, 0.18 amps. 2.80 volts, 0.20 amps. And there we go, last data point, 3.11 volts, sorry, and 0.21 amps. And our bulb is very bright now. When we were taking those first data points, I don't know if you noticed, but the lamp actually didn't light up. Now what we're going to do, because we are good scientists, we're going to see whether the same is true if the current is travelling through the lamp in the opposite direction. So I'm going to turn around my cell, and now we should find that we have negative values of potential difference and current. So in the same table, continue on with your data, but this time we're going in the opposite direction. We're looking at negative values. So I have my first value, my lamp isn't lit, minus 0.20 volts and minus 0.08 amps. Still not lit, and I have minus 0.33 volts, minus 0.09 amps. Still not lit. Oh, no, there's a tiny, tiny glow. You probably can't see it, but I can just see a tiny glow in the lamp now. So we have minus 0.64 volts and minus 0.10 amps. Minus 0.84 volts and minus 0.11 amps. And then if we add in a second cell, there we go, increase our resistance again. We have minus 1.034, where's it going? 4, 3, 4. Minus 1.04 volts, minus 0.12 amps, minus 1.17 volts, minus 0.13 amps, minus 1.40 volts, minus 0.14 amps, minus 1.70 volts, minus 0.15 amps, minus 2.07 volts, minus 0.17 amps. And then if we add in our final cell, making sure we get it the right way round, otherwise it'll be like we've only got one cell, won't it? So nice and bright now. We've actually come back down in our values. Don't worry about that. Just make sure when you're plotting them on your graph, you put them in the right spaces. So you just use your normal scale and add your values in. These values are perfectly valid. Minus 1.75 volts, minus 0.15 amps, minus 2.04 volts and minus 0.16 amps, minus 2.31 volts, minus 0.17 amps, minus 2.55, oh, that's gotten to 5.6, minus 2.5, let's settle down, minus 2.57 volts, minus 0.18 amps. Let's do one last one, minus 2.96 volts, minus 0.20 amps. And there you have it. That is your full set of data. Now, what you'll need to do is to plot a graph with current on the x-axis and potential difference on the y-axis. And you're going to need to make sure that in your graph you've got space for negative values as well as positive values of both of your data. And then you'll need to draw a line of best fit. And one of the points that you have on this graph is that when the potential difference is 0, the current is 0. So you can put your line of best fit through 0, 0 in the centre of the graph. Make sure you choose an appropriate scale. We don't want any 3s or 7s or anything nasty like that. Just nice, simple 1s, 5s, 0.1s, 0.5s. That way you can use the graph paper easily in order to be able to plot your points.